We now study the properties of relations. So we look first at a directed graph. So this one right here. So there are three things we can notice. First, look. Each point of the graph has an arrow looping around from it and going back. Right? So 4, right? So 4 goes to 4, 7 goes to 7, 2 goes to 2, 3 goes to 3, 9 goes to 9, 6 goes to 6. This is known as reflexivity. Next, in each case where there is an arrow going from one point to a second, there's an arrow going from the second point back to the first. Right? So here we see, right, 4 goes to 7, so 7 goes to 4. 3 goes to 6, 6 goes to 3, 3 goes to 9, 9 goes to 3, 6 goes to 9, 9 goes back to 6. This is known as symmetry. And finally, in each case where there is an arrow going from one point to a second point, and then from that second point to a third, there is an arrow that goes from the first point to the third point. So here we see 3 goes to 9, 9 goes to 6, so 3 goes to 6, 9 goes to 6, 6 goes to 3, so 9 goes to 3, 6 goes to 3, 3 goes to 9, so 6 goes to 9. And this is known as transitivity. These are the three properties of relations, and we now formally define all three. So we let R be a relation on a set A. R is reflexive if and only if for every x in A, x is related to itself. R is symmetric if and only if for every x and y in A, if x is related to y, then y is related to A. I'm sorry, y to x. And third, R is transitive if and only if for every x, y, z in A, if x is related to y and y is related to z, then x is related to z. So we have a finite set here. We have the set of 0, 1, 2, and 3. We define three relations, R, S, and T, on A as follows. R is 0, 0, 0, 1, 0, 3, 1, 0, 1, 1, 2, 2, 3, 0, and 3, 3. S is 0, 0, 0, 2, 0, 3, 2, 3. T is 0, 1, and 2, 3. So we want to determine whether each relation is reflexive, symmetric, and or transitive. So we're going to do this by drawing directed graphs. Right? We can draw a directed graph because this is a finite set. So there's 0, there's 1, there's 2, and there's 3. So let's start with R. Right, so we have 0, 0, we have 0, 1, we have 0, 3, then we have 1, 0, 1, 1, 2, 2, 3, 0, and 3, 3. So we check, is it reflexive? Well, every point has a loop arrow around it. So R is reflexive. Is it transitive? So if there's an arrow from one point to a second, is there an arrow that goes back? Well, 0 goes to 1, 1 goes back to 0, 0 goes to 3 goes back to 0. So R is also symmetric. Finally, is it transitive? So if an arrow goes from one point to a second point, and then from a second point to a third point, is there an arrow that goes from the first point to that third point? Right, so we have here 0 goes to 1, but 1 doesn't go anything. 1 goes to 0, 0 goes to 3, but there is nothing 1 to 3. So R is not transitive. Let's look at the directed lines, the directed graph for S now. So 0, 1, 2, 3, 0, 1. So we have 0, 0, 0, 2, 0, 3, and 2, 3. So is it reflexive? Well, the only point that has a loop arrow is 0, so R is not reflexive. Is it symmetric? So 0 goes to 2, but 2 does not go back to 0, so no, it is not symmetric. Is it transitive? Well, let's see. 0 goes to 2, 2 goes to 3, so 0 goes to 3. 0 goes to 3, but 3 doesn't go to anything. 2 goes to 3 again, 3 doesn't go to anything, so yes, R is transitive. Let's finally determine the last one. 1, 2, 3. That's bad looking too. There we go. So it's 0 goes to 1, and 2 goes to 3. Well, there are no loop arrows here, so R is definitely not reflexive. So 0 goes to 1, but 1 does not go back to 0, so it is definitely not metric. Zero goes to 1, 1 doesn't go to anything, 2 goes to 3, 3 doesn't go to anything, so R is transitive by default. Right, so you have to remember, transitive says if a point goes to a second point and that second point goes to a third point, then the first point goes to the third point. We have no situation where we have a point going to a second point and that second point going somewhere else. So it's automatically transitive. Well, now let's look at an infinite set. So define a relation on the real numbers as follows. For all real numbers x and y, if x is related to y, x is related to y if and only if x is equal to y. We're asked to determine whether this is reflexive, symmetric, or transitive. Okay? So let's start with reflexive, and we say let x be a real number. Well, clearly, x is equal to itself. which means x is related to itself, which means R is reflexive. Now, let x and y be two real numbers such that x is related to y. By definition of the relation, this means that x is equal to y, but this would mean that y is equal to x, which means that y is related to x, which means R is symmetric. Finally, let's look at three real numbers, x, y, and z, such that x is related to y and y is related to z. Then we would have x is equal to y and y is equal to z. But this would mean that x is equal to z, which means that x is related to z, which means R is transitive. So this relation, which happens to be called the equality relation, is symmetric, reflexive, and transitive. Now we're defining R to be x is related to y if and only if x is less than y. Alright, so let x be a real number. Obviously, x is not less than itself, so this means that x is not related to itself. So R cannot be reflexive. Now let's look at real numbers x and y, such that x is related to y. Then this would mean that x is less than y, but that would mean that there's no way that y can be less than x. So this means that y is not related to x, which means that R is not symmetric. Now let's look at three real numbers, x, y, z, such that x is related to y and y is related to z. Then x would be less than y and y would be less than z. This would mean that x is indeed less than z as well. So we have x is related to z, which means R is transitive. Now this relation is known as the less than relation. So the less than relation is not reflexive, not symmetric, however it is transitive. And now let's look at a relation T on the set of integers, defined as follows. For all integers m, n, m is related to n if and only if 3 divides m minus n, and determine whether this is reflexive, symmetric, or transitive. Alright, so let m be an integer. Then m minus m is equal to 0, which you can write as 3 times 0. This means that 3 divides m minus m, which means that m is related to m. Should be using a t, not an r. This means that t is reflexive. Now, let m and n be two integers, such that m is related to n, then 3 divides m minus n, which means that m minus n would be equal to 3 times some integer q. This would imply that n minus m is negative 3q, which we can write as 3 times negative q. But negative q is an integer, so this means that 3 divides n minus n, which means that n is related to m, and so t is symmetric. Now we're going to look at 3 integers, m, n, and p, let's say, such that m is related to n and n is related to p. Then this means that 3 divides m minus n and 3 divides n minus p. So this means m minus n is equal to 3 times some integer q1, and n minus p is equal to 3 times q2 for some integer q2. This would mean that n is equal to 3q2 plus p, which would mean that m minus n is now equal to m minus the quantity of 3q2 plus p, which equals m minus p minus 3q2, but this has to equal 3q1. So we have that m minus p is equal to 3q1 plus 3q2, which is 3 times q1 plus q2, and q1 plus q2 is an integer. So this means that 3 divides m minus p, which means that m is related to p, which means t is transitive. Now, this relation, known as the congruence modulo 3 relation, is reflexive, symmetric, and transitive. We will actually be studying the congruence modulo relations in a future lecture. However, I do want to point out right now, look, so we had this t was all 3, and this r was all 3. If a relation is all reflexive, symmetric, and transitive, then we give it a special name. It is then called an equivalence relation. And that is what we will be looking at in the next video. So that concludes our look at the 3 properties of relations.